Hello all. We are here to explore the topic from 12th maths called relation. So relation is all about connecting elements. In maths, relation describes connection between elements of sets. A relation is a way of associating elements which are from one set to another set, often based on certain properties or rules. Relations are fundamental in various areas of mathematics like algebra, geometry, graph theory. We'll next discuss different types of relations and examine the properties of relations that satisfies each and every one. But before we start, let's revise the connecting topics like Cartesian plane and Cartesian product. Cartesian plane, also known as the coordinate plane, is a two-dimensional plane formed by the intersection of two perpendicular lines. So this is x-axis, which represents the horizontal line. This is y-axis, which represents the vertical line. And the intersection of the two axes gives the origin of the plane. The whole Cartesian plane is divided into four quadrants. So this is our first quadrant having the sign plus and plus. This is the second quadrant which represents the coordinates as minus and plus. This is third quadrant which has the coordinates with negative sign. Both coordinates are with the negative sign. This is the fourth quadrant forming by the positive and negative coordinates. Each point in the plane is represented by an ordered pair which can be written as x, y. Moving on to Cartesian product, it is all about combining sets. The Cartesian product is a fundamental concept in maths that allows us to combine two or more sets in a very specific manner. The Cartesian product name is given after the name of a French mathematician and philosopher, René Descartes. The Cartesian products help us to create new sets by pairing the elements from set A to the elements in set B. So let us explore the pattern it forms when two sets are combined by Cartesian product. The Cartesian product of two sets. Suppose we have a set A having element A, B and C in it and set B having element 1 and 2 in it. So it is formed the Cartesian product from A to B is the linkage of each and every element of set A to set B. So Cartesian product of A cross B can be written as A when linked to 1, B linked to 1, C linked to 1, like A1, A2, B1, B2, C1, C2. That's how these are linked, each and every element from set A to set B. Cartesian product of A cross B, thus be formed by like this. These are the various ordered pair which are the Cartesian product is shown. Each element of a Cartesian product forms the ordered pair, where the first component is from set A, the second component is from set B. Now we are all set to move ahead with topic relation. Relation is a way of describing a relationship or connection between the elements of set A to the set B, or like one or more set. It is a fundamental concept that helps us to model and analyze the relationship between objects and quantities between the sets. So relation R from set A is always relation R from set A to set B. Relation R from set A to set B is always a subset of Cartesian product of A cross B. Cartesian product of A cross B can be shown in the format of 1p, 2q, 3p, 4s, 4r. These are the certain ordered pairs from the Cartesian product of set A and set B. So A cross B is basically the ordered pair that satisfies certain condition or product. It can have all the elements or few of them from that. Element from set A always forms our domain like 1, 2, 3, 4. These are the elements that are from set 1. These forms are domain, and the elements from set B which are linked to the certain relation forms our range, like P, Q, and R. We often write relation as X related to Y, or XY belongs to R, that completely indicating X and Y are related to each other. Now we have a dedicated formula to calculate the number of possible relations from set A to set B. Formula goes like 2 to the power mn. What's m? M are the elements of the domain, which is our set A. N are the elements of the range, which forms our set B. So this is how domain and range build up. Now moving ahead with the special types of relations. Certain relation exhibits unique properties that makes them particularly useful and interesting. With the help of these, we can make and analyze, we can model and analyze a specific relationship between the elements. So here are we with some special type of relations. The first is reflexive relation. Reflexive relation is a type of relation where each and every element is related to itself in a loop, or the ordered pair is doublet. Next, we have symmetric relation. Symmetric relation is a type of relation where the relation is mutual between two elements. It is consisted of two elements, X and Y. X is related to Y, then Y must relate to X. Next, we have transitive relation. It is a type of relation which is passed through a series of chain of elements. Like a chain of element is built up in between three elements, X, Y, and Z. Last is equivalence relation. A relation becomes equivalent when it combines all the properties of reflexive, symmetric, and transit. Let's discuss this special type of relation separately. So first we'll go ahead with reflexive relation. A relation R on a set A, relation R on set A is said to be reflexive if and only if each element of A is related to itself, like we have provided with element A here. So A comma A belongs to R. For all A belongs to set A. A comma A belongs to certain relation for all A belongs to set A. Key property here is for that every element should relate to itself in loop, and ordered pair should consist of doublets. Ordered pair should consist of doublets and relation should be with itself. Okay, so there are some examples which are related to reflexive relation. It is equal to obviously gives us a reflexive relation, is greater than equal to, is divisible by, is similar to. Another counter relation to reflexive relation is irreflexive relation. Irreflexive relation is a type of relation where element is not related to itself in a loop. For example, we have P here. So P comma P does not related to itself for all P belongs to set B. So this is a irreflexive relation. No element relates to itself. Example for this is smaller than or greater. In maths, reflexivity is one of the fundamental property used to classify relations, particularly in a very fundamental manner. So when it comes to studying equivalence relations and partial order, one specific type of reflexive relation is identity relation. The difference between reflexive and identity is the only about the element. Suppose set A is consisted of three elements and ordered pairs for reflexive relation forms like A to A, B to B, and C to C. So all the elements that are present in set A should relate to itself, forming order pair of uh, them with themselves. Then the particular relation forms identity relation. Otherwise, it is a reflexive relation. So let us discuss an example for the same just to prove the reflexivity of a relation. Example here is relation R is a set A consisted of certain elements. Relation X and Y, X is related to Y where Y is divisible by X. So let's verify the condition for the divisibility test or divisibility one here. We are taking two elements from the set A. Let's take 2 and 3. Okay, so 2 is divisible by itself. So therefore 2 comma 2 belongs to set relation. 3 is divisible by itself. A number is always divisible by itself, no doubt. So 3 comma 3 belongs to relation. So here we are uh, in a state of proving, or we can say the elements in the set are related to itself. It is like completely clear with this. Moving on to second type of relation, it is symmetric relation. It is a type of binary relation where an element A and B lies in set A. A and B belongs to set A, and A is related to B in some way. A is related to B in some way. Then B should relate to A in the similar manner or in the similar way. A related to B. If A is related to B, then B should relate to A in the similar way for all AB belongs to set A. Example for this are is equal to, is a sibling of, is married to, is parallel to. So these are certain examples which gives us a symmetric relation between the two sets. The counter relation for reflexive relation is asymmetric relation. Asymmetric relation justifies for all AB belongs to A. If A is related to B in some way, then B should not relate to A in the similar way. If A is related to B in some way, then B should not relate to A if belongs to relation. These are not related to B in the similar way. A is related to B in same way, then B should not relate to A in the similar way. Example for a symmetric relation is a parent of greater than divisible by. There are few examples. So let's check the symmetric relation for the similar example we have chosen earlier, where R is a relation between X and Y, where Y is divisible by X. So taking two numbers from set A, say 2 and 4. Okay, so 4 is divisible by 2. So ordered pair for this would be 4 comma T. 2 belongs to relation R. But 2 is not divisible by 4. So ordered pair for this would be 2 comma 4 would not be related to each other. So this is not a symmetric relation. Moving ahead for the third type of relation is transitive relation. So transitive relation is a type of binary relation where three elements are associated to it. Like when A and B are related to some way, B and C are related to similar way, and A and C should relate in the same manner as AB and BC are related in relation. For all A, B and C belongs to set A. A relates to B in some way, B relates to C in the similar way, then A should relate to C in the similar way. So example for this transitive relation are is equal to, a number is equal to itself, is greater than, is divisible by, is a subset. Some key points should always be remembered when we are solving for transitive relation. Number one is, if I happen to find only one pair from the three in the set, what are the three pairs? It's A comma B related to relation, B comma C related to relation, A comma C related to relation. These are the three pairs which we need to find for a transitive relation. If we have only one pair in our set out of three, then it vacuously satisfies the transitive condition. It automatically becomes a transitive relation. Second point is, if we happen to find only two pairs, if there are only two pairs present in the relation for proving transitivity of a relation, then that already implies that the presence of third pair must be there. If two are there, we can consider the presence of third pair as well. So this will become transitive itself. So let's discuss the similar example for the transitive relation. We have three. Let's take three variables for three numbers from set R to prove the transitivity of a relation. Let's take 1, 3, and 6. So 6 is divisible by 3. Therefore, 6, 3 belongs to relation. 3 is divisible by 1. So 3, 1 belongs to relation. Then 6 should be divisible by 1. So therefore, 6, 1 should relate to the relation. Therefore, this is a transitive relation. Moving on to last relation, which is an equivalence relation. An equivalence relation is a type of relation which satisfies the binary relation between a reflexive, symmetric, and transitivity of a relation. Okay, so it is a type of relation which can justify all the three types of relation, becomes an equivalence relation. So with this, we wind up with our today's topic. Hope you all like it. We'll come soon with some more videos of the explanation. Bye bye. See you soon.